Yes, hello, GOTO Oslo. Thank you for signing up for this talk. I hope you do enjoy it, even though it's being streamed. My name is Mark West, and I'm an Englishman living here in Oslo, Norway. And I'm going to be talking about data science today. I'm going to be talking about some of the theory and some of the practice behind it. And just to introduce myself, for those of you who don't know who I am, I'm actually a Java developer and architect who, for the last maybe 2 years, has actually been building up a team of data scientists at my employer, Bouvet, in Oslo. So it means that I'm coming to you today from the perspective of a system developer who's taught himself all of this data science nonsense. And in my spare time, I'm actually the leader of JavaBin, which is a Norwegian Java user group. There are 3,000 of us today, and we arrange a conference called Java Zone each autumn in Oslo. So my talk pretty much today looks like this. There's 3 sections. The first one is what data science is. So that's defining what data science is, talking about the skills you need, the competencies you need, the teams, the processes, all that good stuff. And then I'm going to focus on some machine learning algorithms for you. So I'm going to go through 3 commonly used machine learning algorithms that data scientists use, and I'll explain how they work. And then finally, we'll go through a practical example at the end of the talk where I tie everything together. So, what is data science? Well, when you don't know what something is, what do? You Google it, and then you end up going down the rabbit hole and end up at Wikipedia. Wikipedia has a nice little definition of what data science actually is. Wikipedia says that data science is an interdisciplinary field of scientific methods, processes, and systems to extract knowledge or insight from your data. Now, this is a lovely quote. It doesn't mean a lot on its own, so let's drill down into some of these words. We'll start with the word interdisciplinary. What does that mean? Well, when you work with computer programming, for example, you often have a background in computer science. You maybe have education in computer science. Maybe you have experience in computer science. And what you do is you take that and you combine it with domain knowledge of your customer or your employer, and what you do with this is you create beautiful software. So you combine computer science knowledge and domain knowledge to create beautiful software. And my argument here is that you need these 2 things to work with data science. You need to be able to write code. You need to understand the domain you're working with. But in addition, you need to have math and statistics skills. You need to be able to understand how the algorithms work. You're working with large amounts of data. You're working with predictive statistics, descriptive statistics, so you need to understand the theory behind that as well. So these are the skills that you need to work with data science. The next word I want to look at in my quote is a scientific word. What does that mean? Well, the scientific process is well defined, and it normally starts with a question. You have a hypothesis or a question. So when you start a data science project, you should always start with a hypothesis or a question. What are you trying to actually prove or disprove with your project? And that actually takes a while to define. To make a good hypothesis is not easy. It takes effort and time. So once you've defined that hypothesis, you then need to go out and you need to gather your data. You need to go to all those grumpy system owners and you need to get them to open up their APIs so you can get their data, or ask them to give you a data dump. That will take time. And if there's lots of data from disparate sources, it will take even longer. And once you've gathered your data together, then you're ready to go to the next step. And that is your exploratory data analysis. In this stage, what you're going to do is you're going to take a deep dive in your data. Is your data good enough? Is the quality good enough? Is the data missing? Is there duplicated data? Can you answer the question you've asked with the data you have? And that's what the exploratory data analysis phase does. And at this stage, you're often using basic machine learning methods to give you insight into the data. Now, these first 3 steps here are 60 to 80% of the data scientist's job. This is what you're going to spend all your time doing. It's not going to be creating cool algorithms and neural nets. It's going to be understanding the data. And if you skip this, you'll get worse results. The next step, after you have your data, once you've done your exploratory data analysis, then you're ready to actually start building your formal models. So the model that is going to actually solve your question. And this can itself be difficult because the results you get from this phase may not be very easy to understand. So you may have to interpret the results and work out, okay, do the results actually, are they positive, are they negative, are they conclusive, all that good stuff. So that's step number 5, interpretation. Once you've interpreted your data and you're ready to communicate your data, then you have to communicate it to your stakeholders, which may mean that you have to put your data into a format, or your story that you're telling into a format that your stakeholders can understand. And then you have your result. Now, this is drawn up as a sequential process. In reality, this is an iterative process where you are hopping backwards and forwards between all of the steps as needed. You might get to step number 3 and realize, I don't have enough data. Or you might get to step number 3 and realize, this question, I can't answer it with the data I have. I need to reformulate my question. So the thing to remember here is that this is not a sequential process. It's an iterative process where you can hop backwards and forwards between all of the steps. But we haven't covered one thing. When we looked at that process there, we were missing something, and that is how we get this stuff into production. And this brings us to the next slide then, the roles that we need in a data science project. Now, you need a data scientist, right? That's obvious. But in addition to your data scientist, you need somebody who is going to put this stuff in prod. You need somebody who's going to integrate all of these data sources into a data pipeline that you can use for your training data. You're going to need somebody who's going to monitor your data and also monitor the results and the performance of your algorithms. And this is the data engineer. It's a very, very important role. And I would say in a data science project, they're just as important as a data scientist. You're also going to need somebody possibly to do data visualization, because if you're going to communicate your data in some kind of dashboard or some kind of storytelling or some kind of visualization, you're going to need somebody who understands that area. And that area is actually quite a difficult area, to when you have like a big Excel sheet, boiling it down to something, a simple infographic is an art. And that is where you're going to need your data visualization expert. You're going to need a process owner to tie all this together. The process owner is going to be the project manager. They're going to maintain your stakeholders' expectations. Your stakeholders are going to have big expectations of this data science project. So you need somebody who can maintain their expectations. You need somebody who can maintain a vision, who can keep the team working in the same direction. Somebody who can facilitate, who can deal with those difficult system owners when they won't give you access to their database. And also somebody who can go around in your organization and say, hey, look, this is our data science team. Look at what they're doing. This is big stuff. So back to our Wikipedia quote, data science is about extracting knowledge from data. Well, what does that mean? It's very easy to get confused here and actually think that, like, okay, isn't data science just rebranding of business intelligence, right? I mean, business intelligence is about extracting information from data. But this question, when people ask me this, is data science just rebranding of BI? Well, I answer no, because definitively no, actually, because in my eyes, data science is an evolution of BI. What data science does is it builds upon BI to give us even cooler stuff. So we can look at different ways in which data science builds upon BI. One is data sources. So traditional BI focuses on structured data in data warehouses, whereas data science adds the ability to work with unstructured data. So business intelligence is all about, relational database management systems, whereas data science allows us to work with log files, audio, images, emails, natural language, all that good stuff. When working with business intelligence, we often have a focus on visualization of data and statistics, but data science adds the ability to work with machine learning. And this, in turn, gives us more possibilities. The goals of business intelligence are always about steering the ship. Based on what happened last month, what should we do this month? Whereas data science is more about, hey, we can really improve your organization through this advanced functionality. When I'm talking about advanced functionality, I'm talking about self-driving cars. I'm talking about automatic translation. I'm talking about speech to text. I'm talking about image processing, face recognition. All of that is outside of the remit of business intelligence and more data science thing. And when we're talking about machine learning, let's put machine learning into context, right? There's a lot of confusion about what machine learning actually is, especially in relation to AI, deep learning, all that good stuff. So AI is about enabling computers to be like us. And AI is a very broad field. When I studied AI back in the 90s, I had linguistics, I had philosophy, I had psychology, and I had computing. So AI is a very broad area. What we're doing in industry when we're creating like predictive models, descriptive models, we're using machine learning. And machine learning is about using algorithms. It's about defining and implementing algorithms that allow computers to learn, that allow them to make predictions, that allow them to describe data without them being told how to handle that data. And then we have deep learning. Deep learning is a specialization of machine learning which focuses on neural networks. But we're not going to talk about deep learning today, I'm afraid. We're going to focus on simpler machine learning algorithms. So we're at the end of the first part of the talk now. So what is data science? Some key takeaways. Data scientists require math and statistics skills in addition to skills in software development. This is because they need to understand the statistics methods and the algorithms that they're going to be using. Data science is hypothesis driven. You start with a question and then you try and prove or disprove it. Data science projects require a range of competencies and roles. So, they require more than just a data scientist. You need a data engineer, you need a visualization expert, you need a process owner. And it is possible for one person to take on more than one role. So the data scientist can also be a good data engineer. They are around, they're difficult to get hold of, but they can be found. And then finally, data science can be seen as an evolution of business intelligence. It's the next step. It provides additional capabilities through cutting-edge technologies like machine learning and unstructured data. Okay, now we're ready with part 2 of the talk. Now we're going to look at machine learning algorithms. And just to remind ourselves what machine learning actually is. Well, it's a field of study that gives computers the ability to learn without being programmed. And in case that confuses you, think about it like this. Like with traditional programming, we basically take our data and we look at our data and we understand our data and we work out, okay, how do we want to process the data to get the output that we need to get? Well, machine learning is exactly the same, but we're allowing the computer to find those rules. With machine learning, what we do is we give the computer historical data, historical output, your labels we want it to predict, and we allow it to connect the historical output with the historical input to find those correlations and then build its own rules for processing new data. And one of the challenges with working with machine learning is always the generalized model, because what we want to do is, in most cases with machine learning, we want our model to learn general correlations between input and output that maybe are relevant for all records in our data set, not just for some. And that can be quite difficult. What we really want to do is we want to have a generalized model. And imagine that you have a use case where you want to detect faces in pictures, just any face, not a particular face, but any face. Well, what you want to do is you want to create a generalized model that manages to work out what a face looks like, right? A general face, with the eyebrows, the eyes, the nose, and the mouth, almost like how a child would draw a human face. And what often happens is you don't have enough training data, or your training data is not good enough, or you don't allow your model enough time to learn. And then you end up with an underfitted model that doesn't actually work at all. It doesn't manage to tie your input with your desired output. And then on the other hand, what you can end up with is overfitted. Now, what's happened with the overfitted model is your model has actually memorized the training data. It hasn't generalized, it's just memorized the training data. So what happens there is that your model will only work when you show it training data. If you show it new test data, it'll probably fail because it's learned only to recognize your training data. And that's the challenge with building a generalized model in machine learning. You have to find the right amount of training and you need to stop it before your model gets too good. And it's kind of a sliding scale based on your use case and based on the data you have, a sliding scale whether your model is overfitted or actually working just right. So it's not so easy as you might think. And I'm going to come up with an example of overfitting later on in the talk. So there's 3 types of machine learning out there, 3 general types. The first is supervised learning. With supervised learning, we're building predictive models based on historical data. An example of that might be, like I just said, finding faces. Especially if you wanted to recognize individual faces, you would show your model lots of pictures of people and you would say, okay, this is Mark, this is Peter, this is John, this is Helena, and then you would expect the model to find the correlation between what the pictures it was seeing and the specific labels. That would be supervised learning. Unsupervised learning is a slightly different type of algorithm, which is about describing your data. This is descriptive machine learning. So unsupervised learning is going to look at your data and try and group it together, find patterns, trends, without being told where those patterns or trends actually are. An example of unsupervised learning might be giving your model all of your customer data so that your model can actually group customers together or create customer segments. And then finally, we have reinforcement learning, which is very popular as well. And that's about using a feedback loop from the environment to improve the model's performance. So the model is constantly learning and learning. It's learning, through feedback, what not to do again and what it should do again. And reinforcement learning is often used in game programming, like, when you look at chess program, chess computers, or even stock trading, all that good stuff. But reinforcement learning is quite an advanced topic, so we're not really going to go into that today. We're going to stick with the most commonly used machine learning algorithm types. And we're going to look at machine learning algorithms that are commonly used by all data scientists, often in the exploratory data analysis phase. And these are the types of machine learning algorithm we're going to look at are supervised and unsupervised learning algorithms. We're going to have regression in supervised learning, which is about predicting a value. We're going to have classification, which is about predicting a class. And then we're going to have unsupervised learning. We're going to have clustering, which is about describing our data and grouping it up into similar clusters. The types of algorithm we'll look at are linear regression, decision trees, and k-means clustering. We'll start with linear regression, which is so simple that people don't even understand that this is machine learning, but it is machine learning. And we have an example here of some training data where I have some historical house sales information. So I have the size of the house and the price it's sold for. And the size of the house is our feature and the house price is our label. That's the value we want to predict. So what I want to do is I want to create a predictive model which will tell me how much money will I get for a house based on its size. And because we've only got two variables here, we can plot them in a nice simple two-dimensional graph. And each of these red dots represents one observation, one house that was sold. And we can see here the horizontal axis is showing the size of the house, and the vertical axis is showing us how much the house was sold for. And based on this, we can actually build a machine learning model. And do you want to see the machine learning model? Here it is. That blue line there is a straight line through our data, which is our machine learning model. This is our linear regression model, which will tell us, will allow us to predict new house prices based on this trend line here. So basically we can see that based on this trend line, we can say that, okay, a house that is 5,000 square meters will sell for 1.5 million, right? Now, that's our model and that's our first prediction, but we can also see there are some data points which are actually quite a long way away from this trend line, right? So according to this trend line, we are grossly underestimating the value for a house which was 3,000 square meters. And this is because our model isn't very good. We are trying to predict the value of a house based on its size alone. There are many other variables that go into factoring a house price. The size of the house is one. Does it have a garage? How many bedrooms does it have? Where is it located? Is it in good condition? All of these things will affect the house prices. So our model here is very, very simplistic, which will explain why we have so much deviation, or why we have this deviation, for example, from the trend line. But how is this trend line actually drawn? How does a linear regression model find and draw this trend line? Well, it uses something called ordinary least squares. And what ordinary least squares does is it measures the distance from the trend line to each historical observation, right? So in this case, this example here on the left-hand side, you can imagine that these blue dots are the historical data showing us the size of a house and its sales price. And the red line is the trend line that our model has fitted. And you can see that you can measure the distance between each data point and the trend line. And what you do is you take those values, you square them and add them together, and you get something called the sum of squared error. And this tells us how wrong or right our trend line is overall. And what linear regression will attempt to do is it will attempt to produce a trend line which gives us the lowest sum of squared error. That is the fitting process. So when you fit a linear regression model, it is trying to find the lowest sum of squared error when it draws that trend line. And that trend line has to be straight. This is linear regression, which adds an extra complexity. Another added complexity are outliers. Outliers are data points that are either one-offs, errors, that kind of things. You know, things that don't happen a lot or never normally happen. But the problem is when you're drawing a trend line, an outlier can drag your trend line, away from where it should be. And that's the danger of using things like linear regression, because outliers can definitely skew your trend line away from where it should be. So you need a process or a method for dealing with outliers. First, you need to identify them, and then you need to make a decision. Do you remove them or do you normalize them? So that's basically it for linear regression. Pretty simple to understand, transparent, easy to show. Outliers skew the trend line, and obviously this is linear regression, so it doesn't work with non-linear relationships. Let's look at a different type of machine learning algorithm. Let's look at decision trees. These can actually be used for regression and classification, but in this case, this example, we're using them for classification. And what we'll do is we'll go through a simple example first of how decision trees work. Now, decision trees are just like if-then statements that we program every day. But like when you're using a machine learning algorithm, it has to build that if-then else statement itself. Now imagine I have a data set here. My data set has been given to me by a bunch of recruiters, and this is historical data. Basically, did they make any placements last year? Did they get any complaints last year? Have they ever lived in Norway? And did they get a pay rise last year? And based on this information from last year, they want me to build a model that they can use to decide who gets a pay rise this year based on the amount of placements, or based on whether they made a placement, whether they got a complaint, and whether they lived in have ever lived in Norway. So how a decision tree will work out how to build itself, will it be based on the best split? It'll be based on finding the feature that gives the best split on the labels. And this may not sound very, very clear, and I hope it'll become clearer now, because basically what we do is our decision tree algorithm will look at each one of these features and try and work out which splits our data best between those who got a pay rise and those who didn't get a pay rise. So the first one we look at is lived in Norway, and we see here there's not a good split, right? There are people who got a pay rise on both sides who have lived in Norway and not lived in Norway. So this isn't a good variable to make a split on. Complaints, again, not a good variable to make a split on because it's the same on each side. This isn't a good feature for splitting our data between pay rise and not a pay rise. But when we get to placements, there we get our split, right? So the decision tree would say, okay, this decision tree can just be one level deep. We will just decide on whether who gets a pay rise will be based on who made a placement, who didn't make a placement, such as this. Very, very, very simple. Now, this is all well and good, but what happens when you got bad data? What if our data told us to give pay rises to all those British recruiters who got complaints? Yeah? And this is actually something that happens all the time. And this is the thing when you're working with machine learning, you always have to be aware of your training data. Is your training data good enough? And that's where the statistics comes in as well, to remove bias and to make sure your training data is good. Now, sometimes your decision trees need to be more than one level deep, because one feature isn't good enough for splitting your data between your classes. Here I have another example which requires recursive partitioning. So it's not good enough just with one level. And this is a data set which says, should I play golf? Based on the outlook, the temperature, the humidity, and the wind. Okay? So if I feed this into a decision tree algorithm, the first feature it will find that splits our data will actually be the outlook feature. And the reason for this is because all overcast, all of those records that have overcast set to yes, all say play golf, right? So that's the first feature that my algorithm finds that is good for splitting our data. So the next thing our algorithm will do, it will look at all of the records where the outlook is sunny and try and find the feature that best splits those into yes and no, play golf, yes, play golf, no. And that's humidity. Brilliant, okay? And the next thing the algorithm will do, will look at all of those records where the outlook says rainy and try and find the feature that best splits them, which is wind. And now our model is complete. And you see here that I think it's the temperature feature is completely ignored because it's not needed to build a complete model. So that's decision trees. Very, very easy. White box. Very easy to visualize as well. They're robust to outliers, but they are susceptible to overfitting. They can quickly they can quickly memorize your training data if you're not careful with them. And also, where your data is sliced, the quality of data going into them can give you different results. The third type of machine learning algorithm we'll look at is k-means clustering. And this is for unsupervised learning. This is for grouping your data. And here I have a set of data, 150 data points. And from when I plot them like this, it's very easy to see how these 150 data points will be split up. You can see here there are literally 3 groups of information, 3 clusters. But a machine learning algorithm doesn't have our visual system. Our visual system is actually built for doing that kind of thing, like grouping things together, and we have billions of years of evolution behind us, and machine learning algorithm only has maths. So like in k-means clustering, what k is standing for is the amount of clusters our algorithm will try and find, and k needs to be a meaningful number. So we can see there's 3 clusters here, but 2 clusters wouldn't be good enough, 4 clusters wouldn't be good enough, 100 clusters wouldn't be good enough. So we need to find the number which is good enough for k. But how do we calculate k? Well, this is the first thing the machine will do. It will actually use the sum of squared errors. It can use the sum of squared errors to work out what the optimal value for k is. And the sum of squared errors, as you remember correctly from before, is about measuring the distance from each data point to some kind of trend line. In this case, it would be the distance from each cluster member to the center of that cluster. And those values, those distances would be added up, it would be squared, added up together, which would give us a sum of squared error. Which is just like linear regression, like I showed you earlier on. So basically what we do is we will run k-means clustering for a whole range of numbers against our data set. And from that, we will get something called a scree plot. And this will tell us the optimal amount of clusters for our data set. And basically what the scree plot is showing us is the amount of squared errors, the value of the sum of squared errors, against the amount of clusters that are applied to our data set. And what we're looking for is the elbow of this plot. In this case, we have the elbow here, which is 3, which we knew. We knew that, but it's quite cool that the computer can mathematically work that out. Now, the reason I'm using a scree plot here is because visual, but there are other ways which are completely automatic, such as the silhouette coefficient. So you can actually run this kind of stuff automatically without having any kind of human involvement. So now we know that 3 clusters is the optimum amount of clusters for our data set. Now we can actually apply it to our k-means clustering algorithm. And the first thing it does is the algorithm will randomly allocate 3 centers or centroids to our data set. And the next thing it will do is it will actually calculate cluster membership based on the nearest centroid. So all of those yellow dots, they're all in the same cluster. The green dots are in the same cluster. The purple dots are in the same cluster. But you see our cluster centroids are not central anymore. So now we have to move them centrally into our cluster. But then, of course, we need to recalculate our cluster membership again based on the nearest centroid. And then, of course, we need to move our centroids again. And we carry on doing this. After 6 iterations, our clusters and our centroids are stabilized and the algorithm stops. And now we have our 3 clusters clearly defined. So k-means clustering is really, really fast, and it's very, very effective at finding data patterns. But it does assume that our clusters will be spherical, and each data point can only be assigned to 1 cluster. So there are, some downsides to k-means clustering as well. But I hope you get an idea of how you can actually apply it to your data set and how it can quickly give you results. So the key takeaways of the second part of the talk are that there are 3 types of machine learning: supervised, unsupervised, and reinforcement learning. Machine learning is more than neural networks and deep learning. A successful machine learning model needs to find the balance between overfitting and underfitting. It needs to find that just right balance where it's generalized enough but not too generalized. And machine learning algorithms are merely tools. By understanding how they work, you can use them effectively, you can tune them effectively, and you can get better results. Okay, so now we're at the final part of the talk where we're going to go on to the practical example. And the practical example I'm going to be talking about today is Titanic. The reason I'm going to talk about Titanic is everyone knows about it, so I don't have to spend a lot of time explaining the domain and the context of this practical example. I'm going to build a classification model for predicting Titanic survivability. So it's a predictive model using a decision tree. And my hypothesis is that you can predict Titanic survivability based on the age of the passenger, their gender, and their ticket class. And this is a data set. I'm not going to go through all the different values here. I'm just going to point out the ones that I'm most interested in. And that would be whether they survived or not, the class they travelled in, their gender, and their age in years. The tools I'm going to use are going to be scikit-learn and the Jupyter Notebook. So I'm going to be presenting my code in the Jupyter Notebook. My code is in Python and it's using the scikit-learn package for machine learning. So I'm going to go over to my Anaconda, my Jupyter Notebook now. I'm actually going to close my thing there so you can actually see the notebook properly. Let me see if I can get it up. Here we go. Alrighty-ho. So there we have our, so basically I'm going to actually show you the Jupyter Notebook first. So if I just quit out of this. So a Jupyter Notebook is basically something you use in data science for writing your code, but also communicating the process you've gone through, because data science is a process. So I'm going to go through this now and show you how all of this works and what it means. I'm going to put my Jupyter Notebook into presentation mode. And the first thing I do with my data is I actually import my CSV file, my Titanic data set, and display it using something called pandas. And so I've imported my data set here. And if I zoom in, we can actually see some of the data here. We can see the names, we can see all the different data here, whether they survived or not, their age, and so on and so forth. But what's actually quite worrying here is I can actually see that some of the ages are actually missing. They're replaced by a nan, a null value. So my next step is to actually understand how the data fits together. So by actually doing something called describe on my data set, I can actually, using Python, get a good idea of how my data is organized. And what describe does, it basically creates a bunch of statistic values for the numeric values in your data set. So I can see from looking at this, I can see, for example, here that we have 891 records in our data set. But we can see also here that we only have 714 ages. So it means we're missing a bunch of ages. And from here, I can actually say that, 38% of people in my data set survived the Titanic disaster, because the mean value of all the survived values is actually 0.38. The survival value is set to 1 if they survived and 0 if they died. So already I'm starting to learn a little bit about our data. But we have a problem also. We want to use age as a predictor of survivability. So therefore, we need to do something with all those missing age values. I think we've got 177 age values missing from our data set. So how do we handle this situation? Well, the first thing we're going to do is we're going to do something called feature engineering. And feature engineering is where data science really gets cool. Feature engineering is a big job of the data scientist, and it's basically putting together values to create new features. And what I'm going to do is I'm actually going to work out those missing age values. I'm going to work them out by using the name, because all the names include an honorific, Mr., Mrs., Major. And what we're going to do is we're going to calculate the median age for each honorific and then use those to calculate the missing age values. So the first thing we need to do here is we need to extract honorifics. And I'm not going to go into the code here, but we can see if we just zoom in here, we can see the name, and the honorific is the second location in the name. So I just extract that and place it in a new column called honorific. This is feature engineering. The next step is to work out how many honorifics I have. And if I zoom in here, you can see I've got quite a lot of different honorifics. Mr., Miss, Mrs., Master, Doctor, Reverend. There's loads. There's even some weird ones down the bottom like John Keir, Don, the Countess, and so on and so forth. So what I'm going to do is I'm actually going to normalize these honorifics, because I've got lots of like outliers here that I want to kind of maybe bundle together. So what I'm going to do is I'm going to create a map which maps from the honorifics, the original honorific values, to some new values. So for example, everyone who's called Captain, colonel, doctor, major, reverend. They'll all become servicemen. The countess will become lady. Mademoiselle will become miss. Madame will become Mrs. And so on and so forth. And by doing this, I'll reduce the amount of honorifics that I need to work with. And this box plot actually shows that. Now, what this box plot is actually made to show is made to show the age distribution per honorific. But we can see which honorifics we're working with now. We have lady, master, miss, Mr., Mrs., serviceman, and sir. Okay, that's the honorifics I have after washing them. And this box plot here shows us the age distribution per honorific, with the green line being the median value. These dots up here at the top, these are actually outliers according to the box plot. So we can see our median age for lady is 41. The median age for master is around about 7. Median age for miss is just over 20. Median age for Mr. about 30. Mrs. 35. Serviceman about 50. And then sir around about 40. And those median age values will be used to fill in the missing age values. So that's done here. So basically, for all of those ladies missing their age value, we're going to actually put in the value here, which is 40, just over 40, 41, and so on and so forth. So the next step is another bit of feature engineering. We're just going to clear up the categorical value. Today it's set to male or female, so we're just going to convert it to a numerical value where male is 0 and female is 1. And now we're in a situation where we can actually start looking at our data. We can start getting explorative with our data. What is our data showing us? Does our data reflect our hypothesis? Well, the first thing we can do is see we can map the survivability against the class. And we get a nice little chart here, which basically shows us the survivability based against class. Now, first class is the best. Second class is like, second class, and third class is the worst. It's Leonardo DiCaprio. So if you say that survival, if 1 means they survived and 0 means they didn't survive. So what we can see is a higher proportion of people in first class survived and died, whereas in third class, a higher proportion of people in third class died than survived. So this is actually reflecting our hypothesis so far. How about survivability and gender? Again, we see some worrying patterns here. We see that whereas gender is 0 is male, 1 is female. So if we look at the males, we can see that survivability, was a lot lower for males than it was for females. It's the opposite here, Males, like you see here, the majority died, whereas women, the majority survived. And this also reflects our hypothesis, women and children first, right? But what about the children first part? How does that look? Well, survivability and age. Let's have a look. Well, the first thing we had to do here was actually create a new feature to tell us whether a person is a child or not, because age is a continuous value, right? So it wouldn't be a very useful chart if you did it based on everyone's age. So you have to split your data group into children and adults. And I just used the age of 14 as a cutoff point. And when we plot this, adult child versus survivability, we see that the differences aren't that big. More children survived and died, but it isn't as big as you would thought it would be. And I thought about this a while, and I realized that, if you were a young child, and you were traveling with third-class parents, your survivability chance was lower because a lot more people died in third class than first. But I still think that age has something to do with survivability because of the women and children first thing. So I'm going to keep that variable in my data set. So now I'm going to get rid of everything that's irrelevant. So I'm going to get rid of everything apart from survived, the class of travel, the gender, and their age. And then I'm going to split my data up into training, or I'm going to split my data into features and labels. The features are what I'm going to predict on, and the labels the desired result, whether they survived or not. And I'm going to split my data into training and testing set, because you never test your model with the same data you used to train it. You want it to be tested on unique data it's never seen before. And I'm actually going to put aside 25% of my data, of my whole data set for testing. The other 75% is used for training. And now, ladies and gentlemen, now we're going to do our machine learning. We're going to use a decision tree, or build a decision tree, to find the relationship between our features, gender, age, and travel class, and our label, which is survived or not. And there you go. That was it. I just created a decision tree. And as you see, it didn't really take a long time to do, and it wasn't really flashy. We can actually see also here that we have a bunch of hyperparameters here that are actually defaulted when you start a decision tree. You can actually set these hyperparameters if you want to. I didn't do that in this case. I just ran it with the default hyperparameters. And now we can test our model using our testing set. And we see here that our model is around about, it's actually 75% accurate. Not bad. And then we can visualize a model if we want to as well. Actually, this looks quite big. Let's come out of the presentation mode to really get an idea of how big this decision tree is. Look at this. This is a decision tree here. It's huge, right? Look at this. It's massive. And here we have an example of overfitting. We've allowed the decision tree to build itself as deep as it wanted to be. And it means our decision tree has possibly memorized the training data and maybe not so good with its testing data. So what we need to do is we maybe need to try and reduce this overfitting. So let's try something. Let's actually reduce the size of the decision tree. Actually set the maximum depth of our tree to 3. So we do that. We train the model again. And now we test our score model. And now we get 79.8%, nearly 80%. Just by pruning our tree, just by reducing overfitting, we got 5% improvement. And now we can even visualize this new tree. And with a little bit of work, we could actually turn that into something that our customers or our stakeholders could understand. Okay. So let's go back to the presentation. There's just a couple of things I want to follow up in the last part, some takeaways. So scikit-learn and Jupyter Notebooks are very good for all kinds of machine learning. If you want to download this stuff really, really quickly, you can use the Anaconda distribution, so you don't have to download lots of separate open source stuff. The Anaconda distribution will take care of all of the different versions for you. Feature engineering, as you probably saw, was a vital skill for data scientists. If you can't do feature engineering, you're not going to get very far. Domain knowledge is key to succeed. I managed to solve this problem because I understood the domain. I understood the whole thing about women and children first. I understood the whole story of Titanic, as did you guys. So domain knowledge is also very important. Split your data into test and training sets. It's very important to make sure that you don't just check if your model has managed to memorize your training data. What you really want to know is if your model has managed to generalize. And tweaking hyperparameters like I did with the depth of the tree can give you better results, but you need to understand how and be able to explain how your tweak improved the performance. So that was it for my GOTO Oslo talk. I hope you enjoyed it. If you have questions and you don't get a chance to ask them at the conference, tweet me and I'll do my best to answer you. Other than that, I'd just like to say to you all, thank you for listening, and I hope to see you all in person another time. Thank you.